Alright, so in the last chapter we started talking about how to solve differential equations, and we did one example where we separated the different parts and we integrated both sides, and today we're going to take a further look into that idea. So we're going to explore a technique called separation of variables, and we already discussed what this might mean. Separation of what? What are we separating? Which variables are we separating? X and Y, right? We're separating the X's from the Y's, putting them on either side and integrating. Okay, so that's what we're going to look for. Again, we're still looking at solutions to differential equations. Solutions mean if we plug this Y, this function, into the differential equation, we get something true. Okay, so a solution gives us a true statement, meaning usually by true we mean whatever's on either side of the equal sign is actually equal. Okay. All right. So first, we're gonna go through a couple ideas just to get you familiar with how to address this kind of problem, and then we'll introduce more of the separation of variables part. Okay. So the first thing we need to look at is these two terms: the idea of general solutions and particular solutions, which we've already seen. Okay, a general solution usually has a plus c or some other constant, a constant in some way. Okay, a particular solution has no letter constants. It might have a number, but no letter constant. What do we have to have in order to get a particular solution? Oh man, it's still doing this weird thing. Okay, there we go. We'll have to go back to that. Alright, so we'll try that one more time. Alright, so general. Why is it acting weird? Okay, there we go. Alright, a general solution has a constant. A particular solution has no letter. In terms of constants, you have to have an initial condition, and that's usually, x equals blank when y equals blank, or sorry, vice versa. When x equals blank, y equals blank. Okay, so some initial condition. All right, so here's our official text definition way to say this. A function y equals f of x is called a solution of a differential equation. Sorry, there's a typo there. It should be a space between a and differential. If the equation is satisfied when y and its derivatives are replaced by f and its derivatives. For example, y prime plus 2y equals 0. Okay, y prime plus 2y equals 0. If I take this function, y equals e to the negative 2x, and want to check and see, is this a solution? Well, I plug in, what is y prime? If y is e to the negative 2x, what is y prime?
Y equals 1.
Okay, y is given, y equals e to the negative 2x. In that case, y prime is negative 2 times e to the negative 2x. So if I now plug it in to this equation here, I get negative 2 e to the negative 2x plus 2 e to the negative 2x equals 0. Is that a true statement? It sure is. Okay, all I did was I took my y from here and plugged it in there, and I took my y prime from there and plugged it in there. Okay, and I end up with something that's true. Therefore, we can say that y equals e to the negative 2x is a solution. Okay, so we can say that y equals e to the negative 2x is a solution. All right. So that's what we're looking for here. Okay. All right. So this is a specific solution. We would find that even if our solution that we picked had a c out in front, so some constant times e to the negative 2x, it would still work. That would be our general solution. All right. So let's take a look at example 1. Determine whether the given function is a solution to the differential equation y double prime, so second derivative of y minus y equals 0. All right, so there is the thing that we're trying to solve for. All right, so for each of our candidates here, first thing we want to do is find what is the second derivative. Okay, so for 1, y equals sine x. What's the derivative?
Cosine x.
What's the second derivative?
Negative sine x.
Good. All right, for number 2, y equals 4e to the negative x. What is y prime?
Negative 4e to the negative x.
And what is the second derivative?
Negative
Positive 4e to the negative x, right? So you're going to have the negative one more time. All right, the 4 stays the same, and then e to the negative x. All right, and then 3, y equals c e to the x, where c is a constant. The first derivative, c e to the x. Second derivative, c e to the x. It's always going to stay the same. All right, that one's an easy one. Okay, so now that we know these pieces of information, all we really need is the second derivatives and the first derivatives. All right. I'm sorry, the second derivatives in the original function. The first derivatives can go away. We don't really care about those. Okay. So now we're going to take and plug in. Here is this differential equation we're trying to solve. Okay. So we take y and plug in here, and y double prime, second derivative, and plug in here. So for the first one, we would get negative sine x minus sine x equals 0. Is that true?
No.
Not true. Therefore, what do we say?
It's not a solution of the differential equation.
Perfect. Y equals sine x is not a solution of this differential equation. Okay. Going to the next one, we take y equals 4e to the negative x, plug in the y double prime, plug in the double prime, and we get 4e to the negative x minus 4e to the negative x equals 0. Is that true?
Yes.
Okay, then y equals 4e to the negative x is a solution. All right, and then the last one, y equals ce to the x, and plugging that in, this goes there, this goes there. Okay, so y double prime ce to the x minus y ce to the x equals 0. Is that true?
Yeah.
Yes, so y equals ce to the x is a solution. Okay. Any questions on how to check if it's a solution? All right. All right, so now we're going to take a look at how to find a particular solution, all right? In general, all right, if we have a general solution to what we call a first-order differential equation, all right, so a first-order differential equation just has one derivative of y, okay? So dy dx or 1y prime, no second derivative, all right? So first-order differential equation, the answer will be a family of curves, and we've seen that before, okay? And those are called solution curves. And they'll vary by a constant, meaning usually it'll just be a vertical shift. All right, so if we have a function in the form y equals c over x, and it's a solution to this equation, all particular solutions could be found as long as you had some initial conditions, okay? Now, in general, if we have a, in the past, what we've seen is a lot of times we want our independent variable, our x or our t, to be 0 for one of our conditions, and that makes things simpler. It depends on the function. For example, this function, y equals c over x, if x is 0, that's not going to help us find c, right? No, it's not good. It's not in our domain, it's not going to work. So depending on what we have, we would want x to be 1, and that would give us c right away in this case. All right, so let's take a look at how to do that. So example 2, we've got the differential equation here. The first thing we're going to do is verify that y equals cx cubed is a solution. And then we're going to find the particular solution with our initial conditions. Okay, so just like we saw before, let's verify that this is a solution. So our differential equation has a y in it and a y prime. So first thing we need to do is find out what y prime is. Y prime is 3cx squared. Okay, so now we take this and plug it in to our differential equation and see if it makes it true. So y goes there. Oops, I wrote something wrong. This is xy prime. Sorry. Alright, so y, I'll try and fix this a little bit here. Cx cubed is y. Alright, one more time here. Okay, y goes over here, and y prime goes over here. So plugging in, we're going to get x times 3cx squared minus 3 times what y is here, which is cx cubed, equals 0. Okay? So now, factoring or multiplying out, 3cx cubed minus 3cx cubed equals 0. Is that true?
Yes. No. Yes.
Yes, that is absolutely true. Okay, so we can say that y equals cx cubed is a solution. All right, that's the first step. The next step is to find what c is. Okay, so we did that. Now we want to use our initial conditions to find c. What are our initial conditions?
X equals -3 and y equals 2.
Okay, -3 comma 2 is a solution point. All right, so we take that point and we plug it into our function. 2 equals c -3 cubed. All right, in that case, we would get 2 equals 9 times 3, 27c. So c is what?
-27.
Oh, sorry, you're correct. -27c. So c is
-2 over 27.
-2 over 27. All right, we still have not finished because our final answer should be a y equals function, not a c equals. Okay, so final answer, y equals -2 over 27x cubed is the particular solution. Tell me again, what makes it particular? What makes it particular? What did we have to use?
Initial condition.
Right, based on the initial condition. Okay, any questions there? So now that we are familiar with all of the terms that we need to know, so we know what a differential equation is, abbreviated diff-EQ, we know what a general solution is, we know what a particular solution is, we know what initial conditions are. All right. I'm going to run out of space. There we go. Okay, all of these words we need to understand moving forward, okay? Now we're going to introduce this method for solving differential equations called separation of variables. Okay, this is key. When we consider using separation of variables, what has to be true is this. And this looks complicated, but it's really not. All this says is that we can group the x's all together. We can group the y's all together with the y primes. And we might have a constant, and we might have constants in either one. But then we're going to set it equal to 0 on the other side. Okay, so m is a continuous function of x alone, n is a continuous function of y alone, and then you have the dy dx multiplied. All right, as long as you are able to do this, okay, you can separate the x's from the y's. You see the plus sign separates the x's and the y's. All right, so that's the idea, separation of variables. You can separate them by a plus sign. All right, so this is called a separable equation. All right, here are some examples. All right, so we have, again, like we just said, okay, we have all of our x's together here. We have all of our y's together here, and we have a dy dx. All right, when we do that, we can write all the y's together with the dy, so 3y dy. We can move the x squared to the other side and multiply by dx. So now we have a function of y with a dy on the left side and a function of x with a dx on the right side, and that's going to be useful to us. Okay, notice here, this doesn't look, number 2 doesn't look like what we saw, but we can make it, right? We can get rid of this x from being with the y prime just by dividing, okay? So we can end up with y prime equals cosine x over sine x, which we can replace the y prime with a dy dx, and then we can move the dx to the other side, right? By sort of, if we treat it as Leibniz notation, it's like multiplying, even though it's not really. Okay, so we end up with that. What is cosine x over sine x? Cotangent x. Okay, so dy equals cotangent x dx. All right, and then the last one, still, we've got this x hanging out here, but how do we get rid of the x? Divide again. Okay, so now we have a y prime and a function of y, even though it is kind of weird and complicated. And then on the other side, we have a 2 over x. All right, once again, turn y prime into dy dx, and then move the dx to the other side. All right, so now we have just y on this side, just x on this side, and we're good to go. All right, you'll get really familiar with this process. It just takes time. Okay, so here we go. Here's a function that we are going to be able to solve with separation of variables. Okay, we look at it. Right now we see a function of x here. We see an x hanging out over there. We see our dy dx there and a y hanging out there. So we want to get it so the x's are all together and the y's are with the dy. How are we going to do that?
Divide both sides by x. Divide both sides by x.
Okay. Does that, okay.
No, I'm just kidding.
Let's divide both sides by y first.
Yes.
Okay, if we divide both sides by y, now we have successfully put the y, actually I'll do this, y prime over y. We've successfully put the y with the y prime. We've still got the problem of having x's not together. Okay, so now to get the x's, which, sorry, this is an x, divide by x squared plus 4 on both sides. All right, so now I have y prime over y equals x over x squared plus 4. Now notice, in the original way we saw this written, we saw m of x plus n of y dy dx equals 0, such that these were on the same side. In general, what we really use is with x's and y's on separate sides, so of the equal sign. So as long as that's the case, which if you notice here, if you just subtract m of x from this side, you would get the same thing. Is that clear? Okay. All right, now that we have it, all right, so now that we have our y's and x's separated, all right, we are going to change our y prime into a dy dx over y, and on the other side, x over x squared plus 4. Now we can move the dx to the other side. Okay, so now we have just y's on the left, just x's on the right, and we can integrate both sides. All right, once again, I'll point out, when you have dy over y, this operates the same way as dx over x because the variables match. I'll use a different color. Dy, y. So what would the integral of dy over y be? What's the integral of dx over x? What's the integral of dx over x?
dx of x.
What's the integral of dx over x? It's ln of the absolute value of x. So in this case, it'll be ln of the absolute value of y.
Oh, dx over x.
Okay. On the other side, we have, listen. On the other side, we have a similar situation where we have the degree of the top is less than the degree of the bottom. So we probably are going to have an ln issue, okay? So if we call the bottom u, x squared plus 4, what will du be? There, 2x dx. Divide by 2. All right, so we can replace this with du over 2 and the x dx, okay, is there. And then du over 2 replaces that. And then we're left with 1 over u. All right, so integrating that, we'll get natural log of u, which I'll go ahead and plug it in, is x squared plus 4, and then our plus c over here. All right. Okay. The last step in solving this kind of problem is to go ahead and get y by itself. How are we going to get y by itself?
Plugging y with something x.
Nope.
X equals something.
All right. The only way to get y by itself is to raise both sides by e. So e to the ln of something. Okay, that gets rid of the ln. All right, so y equals, and then on this side, you'll notice this, okay, gets turned into
Oh, it cannot be negative.
x. I'm sorry, I forgot my 1/2. Where'd my 1/2 go? Where'd this 1/2 go? There it is. Okay, that 1/2, which can become an exponent on what's inside my ln, okay? So that becomes x squared plus 4 to the 1/2. What about this c? Okay, it's e to the this plus c. So all of that is in my e. So remember, e to the a plus b is equal to e to the a times e to the b. So it actually ends up being multiplied instead of added. Okay, so we write our c out front. It's the same as e to the c, but e to the c is just another constant. Okay, all right, so that gives us our final solution. How would we check to see if that's correct?
Plug it back.
Okay, we could plug it back into our original differential equation. We'll save that for another day. All right.